Hi, I'm Emily Lakdawalla for Vice News, here to bring you the landing of NASA's Perseverance rover on Mars. It's all going to happen and be done in about an hour and 10 minutes. There's nothing anybody back on Earth can do anymore. It's all up to the robot now to guide itself safely from an interplanetary spacecraft down to the surface of Mars into Jezero crater, where it's going to explore an ancient river delta and answer questions about the past of Mars climate and whether possibly there may have been any life on the surface. Won't be able to really answer those questions until the samples that it collects come back to Earth, but it's going to be a fun adventure following this rover across the surface if everything goes well today. So everybody, I'm not a superstitious person, but I am crossing practically every crossable thing on my body, hoping that everything is going to work well today. The plan for today is that the exciting events of the landing really begin to unfold at in about 1 hour from now, when the cruise stage, part of the spacecraft, separates from the main spacecraft, turns it again from an interplanetary into a planetary spacecraft. And so between now and then, I'm going to have two guests to talk with me about the science and the engineering of this mission. And so my first guest will be Bryony Horgan from Purdue University, who's a geologist, and is going to talk to us about the science mission of this wonderful rover that's about to go to Mars. So I think hopefully we have Bryony up on screen now. Hi, Bryony.
Hi, how's it going, Emily?
It's going good. How are you feeling about today?
Really excited. A smidge nervous, but mostly just super excited.
Awesome. All right. Well, first of all, could you please tell the viewers who you are and what you do on the mission, what your job will be once the landing happens successfully?
Yeah, so I'm on the science team for Perseverance, which means I actually get to work with the data and help figure out what the rover is going to do every day. It's incredibly exciting. I'm specifically on the camera team. We call the cameras Mastcam Z. It's the pair of robot eyes that'll be sending back spectacular color images of Jezero and all the amazing geology you'll be interacting with there. And so my expertise is in geology. I'm a planetary geologist, and I study the geology of Moon and Mars, and also geology back here on Earth too.
Excellent. And those Mastcam Z instruments are going to be absolutely fabulous. I actually worked on the team for a little while myself, and so I feel a little bit of pride in that instrument as well. It's not the only camera that's going to be on this rover, of course. There are 25 cameras landing on Mars with this mission. But the Mastcam Z are the primary science cameras and the ones that will be bringing us the most glorious, colorful images from Mars. So, Bryony, I would like to ask you, maybe I have a video that you provided that is going to maybe set the stage for us. We're going to play that video, and maybe you can talk over it and explain what we're looking at as we go into it.
Yeah, let's do it. All right, so this video is showing Jezero crater as it might have once looked 4 billion years ago, filled with water. So this is a period of time in Mars's history when we think Mars would look very different. We think it might have had rivers, lakes, oceans, all of that. And of course, today, as is shown right now, it's a much drier, more arid, much less hospitable plate. Jezero itself, we think, was an open lake where water flowed in one side and out the other side, which made it a very habitable environment. And the reason we think that is because of these big river channels, but also this big delta you can see highlighted in purple. You can see the front of the delta, what it might have looked like once up against the water in here. And so this delta is a great place to go look for signs of ancient life. Because it would have collected, all of the organic material that was on the plain surrounding Jezero, as well as anything that was maybe growing in the lake itself, and collected it down in the bottom of the lake, in the muds at the bottom of the lake. And so it's a great place to go look for concentrated organics, which is one possible sign of life, or what we call a potential biosignature. And so we're very excited to get to Jezero and actually see this incredible delta up close and personal.
Excellent. So, this is a big, complicated mission. I did an interactive session with a bunch of middle schoolers yesterday who were really interested in learning about how, why this particular mission. How does it get selected? How does it go from an idea to a landed mission? And with you in particular here, Bryony, I'd like to know about how you go from what the scientific question is that's motivating the Perseverance mission, and how you go from a question to a package of science instruments.
Yeah, it's a great question. I mean, so with big missions like this, NASA says, we're going to do this mission. Okay, now tell us what instruments you think might be best to actually, figure this out. So the way they do this is actually compete instruments. We had to submit a proposal to put our cameras on board the rover, and there were, dozens of proposals put in for all different kinds of instruments that could help answer the question of whether or not there are signs of ancient life at the landing site, which hadn't yet been chosen. And so NASA selected, a subset of those they thought could work together really well to put on the rover to actually, go out and do this. And it's being a really amazing suite of instruments. We call Perseverance the roving astrobiologist, and she really is. I mean, we have microscopes and can detect organic material at the size of at the scale of a grain of salt. We have these incredible cameras. We have a ground penetrating radar that will tell us all about what's the structure of the rocks underneath the rover, and is there any liquid water underneath us as well. And we have all kinds of incredible, remote sensing instruments that can map mineralogy and chemistry and organics, again, out in front of the rover at a distance. And so it really is, in the end, came together as a really fascinating suite of instruments that will be our toolkit for looking for life on Mars.
So if this mission is looking for life on Mars, what discovery would tell us that there was now or had been in the past life on Mars?
Yeah, so it's hard, right? Because we're talking about microbial life. The time period that, we think Mars was the most habitable was between 3.5 and 4 billion years ago. That's so long ago. That's back, if you think about Earth and what was going on Earth at that time, that's when everything was just very, very simple, microbial life. It really was the dawn of life here on Earth. And so when we think about what kind of life we're looking for on Mars, it is microbial, right? Very primitive life. And so we need to look for signs of microbes, which is really tough, right? They're hard to see. To pick up a rock and see a sign that a microbe was once there is very difficult. And so, but we have the toolkit that'll let us at least, do our best at that with a rover on the ground on another planet 150 million miles away. We can look for things like microbial textures. You can imagine, say, a microbial mat, a big squishy colony of microbes growing along a lake shore. Say it gets cemented in place, sort of fossilized in place by minerals like carbonates or silica precipitating out of that lake. You can imagine that the textures of those microbes at even very small scales can be preserved by that fossilization process. So we'll be looking for things like that. And some of those textures you can actually see with your naked eye. There's a famous kind of rock called a stromatolite. This is a rock that forms usually in concert with biology, with microbes. If you have these microbial mats growing along with these minerals forming on them, you can form up these really big layers over time and actually make this big dome structure with that, when you look at it, it looks like it grew out of the ground. It looks like it had life in it. And so that's the kind of thing we would love to find in Jezero Crater. And the reason we picked this landing site is because we think it has all of the characteristics you need to create that kind of deposit. We don't know if we'll actually find it, but it's definitely, that would kind of be the holy grail of Mars exploration, to actually see with even just our cameras, the kind of textures that might be microbial in origin. So we'll be looking for that. We'll be looking for organic material, and we'll be looking for anything that kind of seems like it can't be just normal kind of rock processes in origin. So weird minerals, textures, organics, kind of all of that together. And really what we want to see is a bunch of those different things together. So we call a suite of potential biosignatures in one rock. And if we see that, you can bet we'll be bringing that rock back to Earth.
So yeah, tell me more about selecting the rocks that you bring back to Earth. Like, you only have so many samples. How do you decide this rock is the one that I want to get?
It's hard, right? I mean, so because it's not just about life. I mean, that's our first priority, is to find samples that we think could contain potential biosignatures to bring back and verify in labs on Earth that we, did or did not see a biosignature, that there was or was not life. But this is also potentially our only shot ever, maybe, to bring back rocks from a well understood site on Mars. If you think back to the Apollo program going to the moon, they brought back hundreds of kilograms of rocks, and that sample suite we are still learning brand new things from today. Having samples from a planet really just, it opens our eyes to so much about not just that planet, but about the formation of the solar system and the Earth as well. And so this is our chance to do that for Mars, right? So we want to get more than just the stromatolite. We also really want to get things like a sample of a lava flow that we can date, right? And actually put a real, hard date on a lot of these geologic processes. When was this lake present in Jezero? It's really hard to tell just from orbital images and looking with the rover to really get like a date, like 3.75 billion years. We need to bring back a a sample of rock that we can do isotopic geochemistry on and figure out how old it is, but all kinds of other stuff too, right? Every question we want to answer about Mars, a sample can help us. And so really it's going to be about balancing, astrobiology with some of these other questions. And we'll be trying to do as much of that as we can with our samples we bring back.
So sorry, I'm going to say curiosity several times during this broadcast because I've gotten so used to talking about that rover. But no, we're talking about Perseverance right now. If Perseverance does not find biosignatures, is a mission a failure?
No, because we're going to learn so much about Mars, no matter what we find, right? And honestly, too, again, microbes, they're so hard to identify. Just in and out crop as a geologist, you really have to have the samples in the lab to tell for sure. So what we're really looking for, sort of our baseline, are rocks that we think have a good shot of preserving signs of life, even if we can't see them with the rover. So things like mineral precipitates and muds from the bottom of lakes, things that we think, even though the rover can't, for example, detect isotopes and things like that they could contain those signatures. And so even if we don't see conclusive evidence for life, there's a good shot that the samples we bring back will. And even if they don't, that's still an incredibly important discovery, right? Because really what we're trying to do here with this mission is understand how common is life in the universe. Right now we have no idea, right, how common life is. We've made some huge strides in understanding things like how common Earth-like planets are, right? That's been a huge discovery in the past 10, 15 years. But we still don't know even how common simple microbial life is. And so NASA's strategy for this has really been to say, okay, well, let's look for signs of life in our backyard. Let's look for signs of life in the icy moons of Jupiter and Saturn, at Mars. Of those, kind of sets, Mars is easier to get to. It has, the same kind of geology Earth does. We think we understand it pretty well. So it's kind of our best shot for finding clear signs of whether or not life ever existed outside of the Earth. And so even a negative result in this case is incredibly important.
Now, when you get those samples back to Earth, who gets to look at them? Is it just team scientists? Is it just US scientists? Tell me about how that process is going to work.
Yeah, so Mars sample return is an international process. Already part of it is being funded and built by the European Space Agency. So really, it's a global endeavor. Samples from Apollo and things, I think they're available to people all over the world. You can if you can justify why you want to look at those rocks, you can get them. And I think the same will be true with Mars samples. Certainly, they'll be available to anybody in the U.S. and Europe who can justify a great reason. What cool thing can you learn about Mars or the solar system from this sample? So they really are. It's a sample set that will be incredibly valuable, not just to us on the team, but really to everyone in the world, all scientists who want to try to figure out these basic questions.
And I guess, I want to bring it back to cameras, since that's, after all, what you're the most expert on. Can you talk a little bit about what the difference between the camera that you use to, take snapshots with is and a science camera? What makes it a science camera?
So the kind of cameras we use on Mars, ultimately the detectors and things, a lot of that is pretty similar to what you have, in your cell phone. One of the big differences is, how precisely it's built. These are just, beautiful instruments, right? I've seen them in person. They're absolutely gorgeous. They're very precisely built. They have really, we call it Mastcam Z because it can zoom. Each eye can actually zoom independently. So we can get, big landscape shots or zoom in, at very high resolution and get, details of what's going on in that rock. The other cool thing we can do that's actually my expertise is use these cameras to get at what the rocks are made of. We can pass filters in front of the cameras themselves to only filter out certain wavelengths of light, and different rocks reflect different amounts and different wavelengths. And so we can use that to figure out, that's a clay and that's a salt and that's we can actually get that kind of information from that data, which is really great. And so that's the kind of work we'll be doing with the images once we get them back.
And just to give people a sense of the time scale of doing science on this mission, obviously getting the first images back is going to be an incredible moment, but how long do you think it's going to take before we start seeing actual science results coming out of the mission?
That's a great question. So it's going to be a little bit of time before we can really get down and do serious science. We have to certify and validate all of the instruments. We also have the Ingenuity helicopter on board, which will be a pretty high priority to get that out and get it flying around and test out that it's a technology demonstration. So giving JPL the chance to show that we actually can fly on another planet. It's really exciting. But once that's all out of the way, we'll be able to really dive in and do really serious science. And that's when I expect, some of the first amazing results to come out. Was there a lake in Jezero? We're pretty sure there was, but verify that, were there lavas that entered the crater? All kinds of cool things like that will be pretty soon to come, I think.
All right. Well, I know you had to get going at noon, so I want to thank you for joining us today and telling us a little bit about the science on the mission. And go Perseverance, go Mastcam Z. I can't wait to see your first pictures, and Godspeed.
Thanks so much. Looking forward to it.
All right. Bye, Bryony.
Bye. Thanks so much.
Okay. So thanks so much to Bryony for sharing us a little bit of the science. I have another guest who's going to be coming on shortly, and I hope he's been paying attention to what's been going on the VOCA, which is the mission control audio that's telling us what's going on with the mission. There shouldn't, hopefully, be anything exciting happening right now. No news is very good news at this point. And so I'll get a little bit of an update from that. I just want to take a moment, a little station identification, to welcome you to the Vice News live stream for the Perseverance landing. I'm Emily Lakdawalla, and I'm a planetary geologist, a science writer, author of the book about Curiosity that explains to you actually a lot of the engineering that's going on with this mission as well. So because they're actually very similar. And so you can look at that to get the detailed explanations of how all of these landing mechanisms work. But if you really want to go to the source, you have to ask a JPL engineer. So I've invited today Aaron Yazzie from JPL, who's a mechanical engineer there. And he has kindly offered to share his time with us until about 12:30, after which I am going to bring up the audio on, I'm sorry, my producer's going to bring up the audio and on the VOCA and explain so that we can actually really listen into what's going on mission control for all the super exciting events that are about to unfold. So welcome to you, Aaron. Thank you so much for joining us.
Thank you so much. It's so good to see you, Emily.
You too. Can you tell our viewers a little bit about who you are and what your role is on the mission and what your roles have been in the past on this mission?
Sure. So I'm Aaron Yazzie. I'm a mechanical engineer at NASA Jet Propulsion Laboratory. That's what I studied, and that's what my kind of official title is. I tend to veer a little bit into mechatronics, a little bit into robotics, and my job morphs into all kinds of things. When you're a mechanical engineer at JPL, you can do so many different things within that field. So in the past, I've worked, one of my earliest missions was Juno, making some ground support equipment for that. And then I started to move right into Mars missions. So I helped Curiosity when I was a young engineer with its entire testing program. We call it qualification model dirty testing. And then I actually got to move into a role on downlink operations for Curiosity for a little bit. So one of the people that got to receive the downlink feed in the morning whenever the rover woke up and gave us the data about what it did the previous sol, we would assess that data and then give a go or no-go decision on if the rover is healthy enough to perform next day's activities. So that was my time on Curiosity. After that, I got to move on to a new mission called InSight, and that's another Mars mission, a Mars lander. That one was sent there to study Mars's deep interior. It was the first time I was given what we call a cognizant engineer role. Cognizant engineers are basically people that they will basically give a piece of the mission to an engineer and say, here's your baby. Here's a bunch of requirements, like make designs for it, test it, build prototypes, do all your analysis, get it reviewed, and just prove to us that the design that you have come up with and that you have built is ready for Mars and ready to do the thing that it's going to do. So it is kind of like a higher responsibility role, and that's something that we mechanical engineers at JPL really aspire to do, is to be a cognizant engineer on a mission. That means something that we get to design and build and touch and deliver to the mission actually flies and goes into space and does something cool. So I built the pressure inlet for the Mars InSight lander. So that's already on Mars. I got to see that successfully work like it was supposed to, and that was career-changing, life-changing to see that happen. And now I work on Mars 2020. I've been working on it for the past 4 or 5 years almost, as the lead engineer for the rover's drill bit assemblies. So we can talk about it a little bit later, but the rover has 3 different types of drill bits. There's 9 total that the rover can use and interchange as needed to gather rock samples and rock core samples and loose rocky material samples to save into tubes that we want to bring back to Earth for further study. We can also abrade the tops of rocks to help our science instruments while it's on the surface. And so I delivered those drill bits a little bit more than a year ago. And since then have joined another round of QMDT work. So I mentioned that I worked QMDT for MSL. I'm now doing QMDT qualification model dirty testing for Mars 2020. And basically what that means is that we have an entire testing campaign where we get to mimic, like recreate Mars's atmosphere here at JPL, put hardware into a giant vacuum chamber, and we can take it to a really cold temperature to mimic Mars's temperature, pump all the air out and make it a low density atmosphere, just like Mars. We can backfill it with CO2. We can put rocks in there that are similar to rocks we might find on Mars, and we have an exact entire replica of the core drill assembly, the robotic arm, and the entire adaptive caching assembly. So we can practice an end-to-end retrieval of a sample from the time that we drill the rock all the way to sealing it up and storing it inside the rover within this giant test bed. And so it takes a lot of work to do that, and so we're finishing that up actually in the next couple weeks.
In other words, you get to play in a sandbox for a living, but it's a Mars sandbox.
That's totally true.
So, I come from a science background, and I know how that path works. I took all my AP science classes in high school, and I studied geology in college, and I studied planetary geology in grad school, and that's that path if you want to do science on a mission. I don't know so much about engineering on a mission. Could you talk to the audience, because I get a lot of questions about this. How do you go about, if you want to be a space engineer, how do you do that? What's the path? Yeah,
so my path was that I got a bachelor's of science degree in mechanical engineering at Stanford and started work right after that. I think that among the people that I work with, it's probably equal parts people who have a bachelor's degree, people who have a master's degree, and people who have a PhD. And it just means that you come in at different levels, and maybe you can start with certain responsibilities. But the time that I've been here, I've gotten about the same experience and can achieve the same types of roles as people with masters and people with PhDs. So it depends on what you feel like your career path might be. And once you're here, it's surprisingly easy to move around and finagle your way into the area that you want to work. So some people really love to work on these giant, big flagship missions like I do. I love to be part of the big public NASA things that I can brag about to everybody. Some people really love to have a small team where they work on a small spacecraft where they get to have a lot of ownership over their designs and not have a lot of managers or requirements or anything sort of bogging them down. So it all depends on where you want to end up. And like I said before, there's a ton of different types of roles that you can fill in when you're a mechanical engineer. I did a lot of stuff with testing, so setting up a big test bed and making sure that the tests you're doing are sound and right. There's also like downlink operations, like observing the mechanisms and observing the health of a rover or a robot. I did a lot of proposal work, so that's like a very early part of a mission where nobody knows what it looks like and nobody knows how massive it's going to be, or what kind of mechanisms you might need. And so I would come up with the first pass of like what something like that might look like and how big it's going to be and give them a cost estimate, that kind of thing. And then you can also be a cognizant engineer and actually design and build things.
So let's get to that. Let's talk about the thing you designed and built for Perseverance. I think we have a little bit of video that you provided. We're going to run it without sound unless you tell me there's good sound effects. So that you can run it without sound. Okay, so go ahead and explain as the video runs what we're seeing in this video.
Sure.
There we go.
Okay, so this is just an animation of basically an end-to-end sample acquisition. So the rover is able to look around it with all of its many engineering cameras, including the Mastcam-Z, including the HazCams, the NavCams, and once it identifies an area that scientists think is really interesting, the rover will drive up to that area, and it can deploy its big robotic arm, which can reach out about 7 feet to touch down a turret, which includes some science instruments, but also a giant coring mechanism. So this coring mechanism is able to use those drill bits that I created and delivered to the mission to drill into rocks. And so what you just saw there was them drilling a core, a rock core, which is about the size of a piece of chalk. So it's maybe about 2.5 inches long and about 1/2 inch in diameter wide. And so once they grab that core, it sort of falls right inside of a sample tube, and they need to get that sample tube stored safely inside the rover. So they pass the bit back inside the rover, into what we call the bit carousel, and then that carousel rotates down where we can pull the tube out from the bottom in what we call the adaptive caching assembly. And so once it's down, the tube has been pulled out with the rock core inside it, we can do a few things with it. We can take some images to see like a little bit of what the rock might look like, and if we got enough, we can take a volume assessment, and we seal it. So that's important. We want to hermetically seal it so that it preserves the sample that we've collected, and it'll stay protected while we store it on Mars. And then each of these tubes can get stored in its special location inside the rover until we find a place on Mars where we can sort of deposit a set of samples where it will stay and wait for future missions to come and get those samples and bring them back to Earth. So
it's mind-boggling just how complex all of that is and how many moving parts there are, and it's a little bit scary. So can you reassure me about the complexity and the number of moving parts involved in making all of the sample collection work?
Right. So it is certainly complex. And aside from science instruments that have incredible technology and capability, just mechanically, our system is probably the most complicated system on the robot. Like we have maybe 3 different robotic systems that have to work well together and pass one thing from the other to the other. In the process of developing that with a team, it's a huge team because it requires a huge team for each of these robotic systems to work. For someone like me and who worked on the bits, and also my friends who worked on the sample tube, like our parts got passed between each system. And so it meant that if there was a design change in one area, it would affect everything down the line. And so that was one of our biggest challenges, was working well together. We had to hold ourselves to some pretty tight tolerances and and pointing accuracies and all this stuff. Like everything had to be very precise. All of our machining had to be done to an extremely high tolerance. It was quite the feat to just manufacturing these parts to make sure that when they're passed from one thing to the other, there wasn't any interference that we didn't account for, or if dust gets in the system, it's not going to completely jam up the entire thing. So those were the kind of challenges that we had to deal with. But the thing that will help reassure you, Emily, is that we have done so much testing. Like I said, I was working on QMDT, which gives us the best idea of how we're going to perform, how this whole system is going to perform on Mars, because it's in a cold environment, because it's in a dusty environment. We just repeat and repeat and drill and drill and drill, and we get so many different samples that we practice end to end, making sure we get it all the way into its storage location. And we try to think of every scenario. We change the temperatures, change the pressures, but also change the different rock types, change the different angles that we might drill at. We might not always drill straight down to the ground. We might come in at a 45-degree angle, or vertical, maybe not so much, but we still test that sometimes. So we're trying to think of any possible challenge that we might come across and create a test scenario for that.
What were some of the challenges? What were some of the things that you had to do the most redesigns around, like things that maybe didn't work at the beginning and that you had to have multiple iterations to come up with something that was reliable?
I'm trying to think of our team's history. There were a lot of things around the coring mechanism. The coring mechanism is just a beautiful piece of machinery. It actually itself involves, I want to say like 3 or 4 unique actuators, motored mechanisms to provide the spindle, the spinning part of the drill. and it needs to do it in two different speeds, like a high torque, low speed, but also a high speed, low torque version of it. And that's because we need to be able to drill, which requires the faster speed, but also we need to be able to break that rock off from the base rock, which requires a high torque. And so there was a lot of design trades in the early stages around how can we flip back and forth between the two? Is it even feasible? Like, do we need to maybe think of a different way to try to break off the rock? Like, what if we can only provide one speed, and then we have to come up with a different type of mechanism that can break off the core from the base of the rock? What they ended up going along with was basically a transmission. They could flip between these two speeds of the coring mechanism. Other things that they had to do is they had a big lockout rod that comes down and locks out the back of the tube while we turn the bit and create that. There's actually an off-centered diameters in between the tube and the bit that's what actually allows us to break that rock core from its base rock. And so we have to lock out that tube somehow. So this mechanism comes down and locks that out. We also have a percussion mechanism. So we actually get a lot of, most of our advancement into the rock, it comes from percussion. We don't actually have too much on spindle because we don't want to wear out our bit. If we only rotate and use the spindle to drill into a rock, we'll wear out the bit teeth really fast and we'll wear out the mechanism very fast. So we use percussion to chisel away. And the more efficient we're able to use both percussion and spindle together, the longer our bits will last. And one last mechanism is our chuck mechanism. So the chuck is what holds the bits. So we need to be able to interchange our bits. And so it'll go in and grab the sleeve of a bit, use it, and then it needs to be able to release and put that away. So all of these mechanisms, not only did they go through iterations of their own, but even just packaging and how they would interact with each other, they all required a bunch of design iterations, layout iterations. We built a couple brass board versions of each of these drills. And each time we learned something new and improved on the design. So it was a very long process.
Thanks for that. I just want to mention, we saw some applause from Mission Control just now. And I know that I promised my viewers that I was not going to talk over the Mission Voca. That will begin. My not talking over them will begin in approximately 13 minutes. In the meantime, if one of my friends could text me and tell me what that applause was for, I'd really appreciate it. So let's get back to drilling, though, which is, I'm really interested. There's lots of different types of materials on the surface of Mars. You have everything from basalt, which is an incredibly hard rock, to sand. Can you sample all of those kinds of materials, or are there some things you positively couldn't drill? What do you need different drill bits? How does that all work?
Yeah, so like you said, the basalt is it's usually the one that we use as our high our challenge rock, basically. Like it's a hard, dense rock, and when you get it really cold, it makes it even harder to drill. So usually we'll do a lot of our tests in that to sort of say, if we can drill in this, then it's likely we can drill in a lot of the weaker, less dense rocks. If you go on the other end of that, though, there's a little bit of a challenge in when things are too, I don't know how to say it, like they're like too weak. They're weakly consolidated. They might crack too easily, because one of the biggest goals that we want is to be able to preserve a rock core. We want to be able to bring back a mostly solid piece of rock core. And so if the rock is too weak, we need to be very gentle about the way that we eat into that rock. And so one of the coolest things about this whole coring mechanism is that it has a little bit of intelligence built into it, so that it can adjust itself based off of what it feels when it's starting to drill into a rock. So if it feels that it's going into a hard rock, it might adjust the way that, or how the intensity of the percussion level, or how quick the spindle is spinning, or how fast we're advancing the feed into the rock. So all of those parameters actually self-adjust. And it's same thing if we go into a weak rock and there's the fear that it might break that rock into too many little pieces, they'll back off a little bit and back off the percussion to make sure that we don't break it up too much, maybe go into a little bit more of a rotary only type of drilling sequence. So those are the kinds of things that we're really trying to test out when we do things in QMDT, is to make sure that we see all the ranges of rocks we might encounter and see how the drill that we have built the smarts into adapts to it.
So Curiosity was able to do quite a lot of drilling until it did start suddenly having a bunch of problems with various actuators on the drill. Can you talk to me a little bit about lessons learned from Curiosity and how those have fed forward into designing Perseverance?
Yeah, I think in general, a lot of those things are hard to avoid. We always run into mechanism problems with anything that we've sent to Mars. One, mechanisms that are sliding and rotating like to be well lubricated, and it's hard to create a lubrication that is not liquid that might just freeze up in Mars's very cold environment. Also, there's just a ton of dust. There's dust everywhere that's going to get everywhere inside that mechanism, and we don't want that can also affect the performance of a mechanism. And so I think there are some lessons that we learned in, one, designing things that keep out dust, the ways that we input strategic little seals and filters and stuff all throughout the mechanism, different types of coating that we might put on it. There are some solid lubricants that we can put on, also some materials that we can make it out of, so that we're not relying on a liquid lubricant, strategic heaters that you can put in there, so that if you can't get away from using some kind of liquid to lubricate something, you can at least maybe heat it up a little bit before you start to use it. Those are the kinds of things that we're trying to work around and use.
I think one of the things that always strikes me about the engineering on these rovers, especially once I see them on Mars, is the fact that every one of them is as advanced a technology as it is, it's also hand built. So, to what extent have your hands been on the mechanisms that are flying to Mars right now?
Yeah, so for the most part, the physical building of everything, I was working sort of adjacent to the core team. There was a whole core team putting together that whole mechanism. I was responsible for delivering bits to that assembly or that team. So I got to come in and help see and observe some of the core build. I was around for a lot of their first tests. Sometimes we would do a fit check. I would bring a bit over and we would chuck it inside the core and make sure that it actually fit. There's another test where when currently as it's flying to Mars, there's a bit that's installed into the core that is we just call it the launch bit, and it's the bit that's going to stay in there throughout launch and landing. It's mostly there just to protect all the insides in case there's any dust that wanted to go in there, but it's not really one of the primary sets of bits that we want to use. And so we actually ended up deciding to make that launch bit look like an abrading bit, because it already looked the same, very similar already. So we thought, well, if there's anything funny that happens and we can't get to a bit right away and exchange a bit right away, we might be able to use this launch bit and use it to abrade rocks. But the nominal plan is that bit will just get dropped on the surface of Mars once we get there, so that it can pick up a new bit, a fresh bit that it will then use for sampling. And so I got to be there for some of the bit dropping tests, which was fun. As far as making the drill bits themselves, I was heavily involved every single step of the way, not just final assembly in a clean room, but every single in-between step, from when we got it machined to doing things like removing the recast layer. A recast layer is something that gets left behind whenever you machine something using electric discharge machining, which basically uses electric discharge to melt metal into a certain shape. It's very precise, but what it does is it leaves a layer of this discharge material that you have to get rid of. And you do that by etching. So you have to etch the inside of it. We have to passivate the inside so it doesn't rust. We coat it in this, what we call titanium nitride. If you look at a picture of the bit, they're actually all gold in color, and that gold color is titanium nitride. We have to coat it in that for contamination control reasons. any type of contaminant that might want to stick to the surface during our flight, during the time that we're driving around on the surface. That coating helps to, it actually, whatever those contaminants we're afraid of are less likely to be able to stick onto that surface because of that coating. So I was going to vendors all the time. I was visiting my parts in the machine shop, in the inspection shop, all the way to the point where we were testing them, assembling them, and I was there to watch all my puppies get loaded right into the flight bit carousel, which was a sad day. Actually, a very exciting and sad day.
So clearly you have a lot, both career-wise and emotionally, invested in this hardware that is currently careening toward Mars at a couple of kilometers per second. How do you feel right now?
I am a ball of nerves. I'm also super excited. Like we built all this stuff to work on Mars, and we haven't yet gotten to Mars. So today is the first day that we will get there, and we can start actually using all this hardware that we built. So that's exciting for all of us. But at the same time, landing anything on Mars is super hard. It's a very thin atmosphere, is really difficult to land heavy things on, and this rover is the size of a VW Bug. So it is nerve-wracking, but as all the work that our team put into it, we definitely did all of our calculations, our reviews, did all our testing to make sure that our parts would work, and we trust that the EDL team did the same. We know that they've been very careful and diligent about testing and delivering something that they are positive is going to work. So we trust them, and we're also optimistic about it.
And I'll interject. EDL means entry, descent, and landing. Those are the 3 phases of landing that we're just about to go through. That only takes 7 minutes from space down to the surface. And yeah, it's I'm certainly scared, and I didn't build anything on this rover. I got to test. I got to help with the testing of Mastcam Z. So that was a very exciting moment for me.
Nice.
Yeah, it's this is very scary, but it's whatever's going to happen is what's going to happen, and everybody involved. I have never met a group of people who are so not only passionate about their work, devoted to making sure it does work, but just intensely creative. The creativity of people who work in space is just astounding. And I like to talk about that because, it's not really the stereotype necessarily for science and technology folks, but actually creativity is so important. And how, Aaron, are there other ways that kind of crops up, that you find that this intense creativity that flows around these missions?
Oh yeah, for sure. Like one of the things when people talk about like, oh, what would you say to children who might want to work at NASA one day? And I think one of the most important things for them is to be a creative kid, more so than being into math and science. Like when I was a kid, I loved to build things, I loved to use my imagination, and I loved art. I think those are what makes me a good engineer, not so much math and science strictly. And even just being able to express ideas visually, or get your ideas across, communicate them through pictures and through any means that isn't just talking, requires creativity and that kind of design thinking.
And yeah, it's everywhere. Like I find that, scientists have to imagine explanations that have nobody's ever come up with before. Engineers have to imagine ways to do things that nobody's ever thought of before. And you also have to imagine every possible way it could go wrong, which right. I think I would have a hard time with just thinking about that. But it's really amazing. The fault handling that you guys come up with is just astounding. As a last question for you, I want to actually ask you about the bolo that you're wearing. Can you tell me a little bit about that?
Yeah, so this bolo is, you might recognize the logo is basically the NASA logo without the writing on it, and it is beaded. It's a bolo tie, and it's beaded. It was gifted to me by my friend Jenna Schmeeding, who is not only a actor and comedy writer, but she's a talented beader. And I was hoping that she would make something like this for me because I do a lot of outreach, and I really loved that it ties in both of my parts of my identity and the things that I love, which is space exploration, working for NASA, but also being indigenous. So I am an indigenous engineer. I'm Navajo. I grew up near the Navajo Nation, and it's a large part of who I am and my passions in life. And one of the biggest things that I really feel passionate about is doing STEM outreach, especially to the Native communities and my community back home. Just in general, Indigenous peoples are not very well represented in STEM due to a bunch of different reasons, with like access to education and access to college and higher education. And even just all the way up to hiring, diversity hiring. So there's a lot of work to be done all up and down the STEM chain to ensure that we make a place for more representation in places, STEM workplaces, especially for Indigenous peoples. And that's one of my biggest passions, is to help increase that representation.
Well, more power to you. I know with your passion and drive and your excellent explanations, you're probably inspiring an awful lot of kids to go towards STEM careers. So thank you very much today for your explanations. Thanks for your service, and good Godspeed to Perseverance. I hope you drill all the rocks on Mars.
Me too. Thank you so much for having me.
You're welcome. All right, so we are now just 25 minutes away from the moment when Perseverance should have wheels safely on the surface of Mars. And so I'm going to ask Vice News to bring up the audio from Mission Control. I don't expect there to be much to be happening at this moment. The first thing I'm really going to be listening for will be happening in about 7 minutes. That's when we expect the cruise stage, part of the spacecraft, to be separating from the rover. I will talk, but I'm also going to be carefully listening, and I will stop speaking whenever I hear an announcement.
As per step 205 in the OCP, we can confirm that MRO has started their first flu.
Copy, EDLCOM.
All right, so that announcement was between the EDLCOM, that's Entry, Descent, and Landing Communication. So that's the person who's kind of in charge of all the interpersonal communications happening during landing. And somebody whose job it is to monitor the relay, the telecommunications relay between the Mars orbiters and Earth. And so they talked about MRO, which is Mars Reconnaissance Orbiter. It's an orbiter that arrived at Mars and it was launched in 2005, arrived in 2006. It's a venerable spacecraft. It has a terrific camera on it called HiRISE.
Has begun. We have stopped our AMAN, started the raw DP for EDL, idled the nav filter and IVP, and we are now propagating via the DIMU. We've powered on our UHF, but it's not yet transmitting, and the anchor has complete. We expect our next anchor to start in 2 minutes.
Okay, so a lot of acronyms there, but basically they're converting the spacecraft from its interplanetary spaceflight mode to landing mode. One of the things they mentioned was DIMU, D-I-M-U, Descent Inertial Measurement Unit. It's a gyroscope that helps them understand where they are with respect to the surface of Mars. And that is an incredibly important piece of hardware on this lander. It is what's going to permit the spacecraft to navigate as precisely as possible to the center of the landing point. Okay, so these announcements just have to do with setting up the computer, turning on various modes of operation. One of the things they have to do is turn off fault protection. So fault protection is where the computer of a rover will go into safe mode. It'll blue screen and just turn the antenna to Earth for communications, ask for help if it runs into a problem. You don't want that to happen during a landing. So you've got to turn off that kind of fault protection during landing. Really, the only fault protection there is during landing is if the computer freezes, it'll reboot. It probably won't help. If the computer freezes during landing, we probably have a new impact crater on the surface. But so far, I don't expect anything like that to happen today. But you certainly don't want that to happen involuntarily. So preventing the computer from stopping everything and asking for help is one of the important preparation things that they'll be doing between now and landing.
DHR event anchor has begun.
So anchor has begun refers to basically
the BCB discharge and charge states.
The anchor has begun refers to sort of a program, a sequence of commands that is operating on the spacecraft that it's cycling through in order to step through the various steps on the landing. It's got a predicted timeline of events on board, and it's the anchor sets up that set of commands for the spacecraft.
Powering on the pyro firing cards.
Pyro firing card will control the little explosive devices that cut connections between parts of the spacecraft, like the back shell and the heat shield.
Right, we're about
So it's an important controller.
From entry interface. The vehicle is currently preparing the heat rejection system that has kept the thermal system cool inside the air shell for about the last 6 months. This will allow the spacecraft to more easily cut the line in upcoming cruise stage separation, which is under 4 minutes now.
So that voice, by the way, is Swati Mohan, who is going to be doing the most explaining from Mission Control.
The Rover Pyro bus.
She was talking about the heat rejection system, which is really necessary if you have a nuclear-powered spacecraft. It generates a ton of heat inside the clamshell. And they were radiating that heat out to space using Freon tubes, and they have to shut that system down and vent all the Freon to space before they separate the spacecraft.
Stage separation in about 3 minutes, 15 seconds by powering off all the devices on the cruise stage in order that they can be safe once the cruise stage is jettisoned.
So the cruise stage is the part of the spacecraft that had solar panels, star trackers, attitude control jets. They have to throw that bit away, leave it to crash on Mars.
Liquid and gas.
And now they're getting ready to vent the HRS heat rejection system liquid and gas in order to get ready for that separation. I thought I was going to be able to have some time to actually step.
Anchor is complete. We will see the next anchor in approximately 3 minutes.
To step through all the events of landing by talking you through the video.
But from entry interface, we are coming upon cruise stage separation in 2 minutes and 20 seconds.
They're giving us a lot of information. Entry interface is a point in time and space where the spacecraft is delivered to the top of the atmosphere. We generally call it hitting the top of Mars's atmosphere, but it's kind of like the von Karman line or something. It's an imaginary boundary. It's an imaginary point in space and time that the navigators have tried to deliver the spacecraft to. And generally they count up landing time from the time that they hit the entry interface. Once we hit entry interface, we will be less than 7 minutes away from landing. So entry interface marks the beginning of the, quote, 7 minutes of terror. All of you who are playing bingo, you can now mark the 7 minutes of terror off on your bingo cards. I didn't make bingo cards, I should have. We're getting very close to cruise stage separation. The spacecraft is spinning.
From cruise stage separation, about 11 minutes, 20 seconds from entry interface.
The cruise stage is spinning right now at about 2 rotations per minute. There's Swati Mohan. She and I have daughters at the same dance school here in LA. That's kind of amazing.
Tones. Telemetry will have stopped.
Telecom is confirming that the spacecraft has switched to broadcasting tones. These tones are received directly from Perseverance, but have very limited information content. We won't receive real-time information until about 9-10 minutes from now, once the Mars Reconnaissance Orbiter starts relaying information from Perseverance. We are under a minute from cruise stage separation, about 10.5 minutes from entry interface.
So they broadcast tones with X-band radio direct from Mars to the giant radio dishes of the Deep Space Network on Earth.
We're continuing to receive tones from Perseverance, standing by for cruise stage separation.
RCS priming.
Reaction control system, getting ready. Those are the rockets. And there she goes.
Cruise stage sep.
We have indication that cruise stage separation has been confirmed by the spacecraft.
The next thing is they'll have to turn off that spin. So they have to use the rockets to spin down.
Perseverance's landing software will wake up and begin the final preparations for entry. The first action it will do is to fire warm-up pulses with its entry thrusters. These pulses ensure that the spacecraft gets the thrust that it wants during entry interface. We're about 9 minutes from entry interface.
The spacecraft spins as it goes through space for stability, but now that it's entering, it has to no longer be rotating and get ready to fly through the Martian atmosphere.
I have confirmation that we got shadowed by the cruise stage as it passed through our beam to the Earth.
So in other words, the cruise stage separated.
That we could see a signal that the cruise stage went between the Perseverance entry capsule and Earth. So we saw a little blip, the data stream indicating cruise stage separation. We have confirmation that the vehicle has started warming up those entry thrusters. Warm-up pulses have begun.
Spin down.
At this point, the spacecraft is trying to stop its spin from the cruise 2 revolutions per minute down to 0, and then will turn to its desired orientation from entry. It will separate the 2 balance mass that has kept it balanced during all of cruise. This will allow the entry capsule to have lift when it enters the atmosphere. We have confirmation that the spacecraft has turned to the desired entry attitude. We're about 7.5 minutes from entry interface.
So this cruise balance mass business is something that made Perseverance and Curiosity's landings very different from previous landings. They have now jettisoned giant blocks of, or they're getting ready to jettison giant blocks of tungsten in order to offset the center of balance of the spacecraft. And it makes the saucer-shaped spacecraft kind of fly like a wing. It can generate lift. And what that means is that as the spacecraft uses its inertial measurement unit to measure its...
The DTE from Radio Science from Green Bank reports carrier lock. You see the carrier on the downlink.
Flight level 1.
Awesome.
We are continuing to wait for entry interface. We're about 6 minutes and 45 seconds from entry interface. We have confirmation from Greenback that they are receiving direct-to-Earth telemetry via that path.
So Green Bank telescope is a giant radio telescope?
Transmitting heartbeat tones. These tones indicate that Perseverance is operating normally and has nothing significant to report.
No news is good news.
We're currently just over 6 minutes from entry interface.
So the as I was saying about the flight, the spacecraft can steer. It does that by rolling around its nose, and as it banks, it can go to the south, it can go to the north in order to steer, and it does these giant S-curves as it's flying through the Martian atmosphere and trying to manage its entry point so that the parachute will deploy at the perfect altitude to get it to land precisely at the center of its landing ellipse.
We're just under, we're about 5.5 minutes from entry interface. We're still receiving heartbeat tones. We expect to continue receiving heartbeat tones until about 5 minutes after entry. At that time, Perseverance will be no longer in view of our antennas here on Earth. About 90 seconds prior to entry, the Mars Reconnaissance Orbiter should begin receiving telemetry from Perseverance and streaming it to Earth in near real time. There are a few expected short outages, such as when we have a plasma blackout or when we enter the peak heating phase. Aside from these outages caused by the plasma blackout, antenna switching, or high dynamic events, spacecraft events, we should have telemetry until about 90 seconds after landing. A plasma blackout is when the signal from Perseverance isn't strong enough to make it through the superheated, super fast air flowing around the spacecraft all the way down to Earth. Once the temperature drops below that peak heating, we do reacquire the signal from Perseverance. We are currently about 4.5 minutes from entry interface. Perseverance continues to report heartbeat tones, indicating everything is nominal.
All right, she explained all that pretty well. I did note that Mars Reconnaissance Orbiter will only be in contact with the spacecraft until 90 seconds after landing. That's not a lot of time. So it is possible we won't get those first images today, but they'll try, I'm sure.
Ready to receive signals from the lander.
Mars Reconnaissance Orbiter has reported that it's ready to receive the signals from Perseverance. It should be in a few minutes here. We're just
Flight Level 1
from entry interface. Around this time, a second spacecraft, MAVEN, should begin picking up telemetry from Perseverance and will continue to record that telemetry until several minutes post-landing. We won't get that data for several hours after landing as it's being recorded and then will be forwarded to Earth later. We are continuing to receive heartbeat tones, indicating that everything is nominal. We're currently at about 3 minutes until entry interface.
There will be several data dropouts from the spacecraft as it goes through heating of the friction of the atmosphere, but also as it tosses away parts of the spacecraft toward landing. So the first thing will be the heat shield. That won't cause an antenna switch, but the back shell will. So after the parachute deploys, when they toss away the parachute and are left just underneath the rocket-powered jetpack of the landing rover, they're going to need, there's going to be a brief blackout there as they're switching from one radio antenna to another.
We are 2.5 minutes from entry interface. Perseverance is to transmit heartbeat tones, indicating everything is nominal.
At some point, we'll stop receiving those heartbeat tones from the spacecraft because the spacecraft is going to go over the edge of Mars as seen from Earth. So we won't have the direct-to-Earth communication anymore between the rover and Green Bank Telescope and Madrid and Goldstone, the other DSN stations, but it will be in communication with Mars Reconnaissance Orbiter, which is relaying the data to Earth after about a 16-second delay. Mars Reconnaissance Orbiter is decoding the data before relay. Meanwhile, MAVEN is recording the data and not relaying it.
2 minutes from entry interface. As it gets closer to Mars, Perseverance is actually being pulled in by gravity and accelerating. By the time Perseverance reaches entry interface point, she should be going just under 5.4 kilometers per second. We're at about 90 seconds from entry interface and standing by for Mars Reconnaissance Orbiter to pick up the telemetry.
So entry, descent, and landing has 3 phases. Entry is with the heat shield. It turns into a fiery ball of fire in the sky. It has to go down from 5+ kilometers per second to just barely supersonic speeds. The parachute will slow it down from supersonic speeds to subsonic speeds. That's the descent part. And then right after it's going to jettison the parachute, it will free fall for about a second, turn on its landing rockets, continue to descend under the landing rockets, and finally lower it on these cables down to the surface. All of that is very similar to the way Curiosity worked, with 2 exceptions. One is that they're using something called a range trigger to figure out when to deploy the parachute instead of a velocity or gravity trigger.
We have confirmation that the Mars Reconnaissance Orbiter is now relaying data from Perseverance. We're about 30 seconds from entry interface. Perseverance is going about 5.2 kilometers per second and is about 190 kilometers altitude above the surface of Mars.
Confirm your jet
There we go. So we have good data from Mars Reconnaissance Orbiter. That means that we'll get details all the way down to the surface.
W on.
5.3 kilometers per second and an altitude of about 150 kilometers from the surface of Mars.
What you're seeing on the screen is a simulation. It isn't based on direct telemetry from the rover, but it's going to show you a really good computer animation of the approach toward the surface. This is from NASA's Eyes on the Solar System.
We have confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface of Mars. The spacecraft is now waiting until it begins feeling the atmosphere of Mars slow it down. Once there is enough atmosphere, it will start controlling its path to the landing target.
Doppler indicates entry into the atmosphere.
Navigation
So
is also
it's slowed down.
confirming that we can see a little bit of that slowdown of the atmosphere on the Perseverance entry capsule. Our current velocity is about 5.36 kilometers per second and an altitude of about 67 kilometers from the surface.
We are probably seeing MRO plasma blackout at this point.
Bank 1 completed.
Bank 1 completed. So they've done one of those big S-turns. They're guiding their way through the Martian atmosphere. They're flying in a ball of fire through the Martian atmosphere.
Doppler indicate reversal, bank reversal.
We have indications that Perseverance is now performing bank reversals in the atmosphere. These are the steps in order to control its distance to the landing target. Perseverance has just passed through the point of maximum deceleration and has indicated that it felt approximately 10 Earth Gs of deceleration.
MRO has lock again.
Doppler indicate reversal. Bank 2 complete.
We saw a small outage of the UHF telemetry from Mars Reconnaissance Orbiter during that peak heating phase, likely caused by the plasma blackout. Perseverance is still continuing to perform bank reversals in the atmosphere to control its distance to the landing target.
Doppler indicate reversal.
Just like a skier going down a mountain. 3 bank reversals.
End of range control, range minus 1.9 kilometers, cross range minus 2.4 kilometers.
Perseverance is going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars. We have entered heading alignment, which means Perseverance is no longer trying to control the distance to Mars, to the target on Mars, but instead is flying straight to the target.
So no more banking. Now it's just slowing. That's what they meant by the end of range control. Now they're doing heading alignment. They're getting aimed in the correct direction to land precisely at the center of that ellipse, or as close to it as they can. And this is a fairly long phase, lasting more than a minute. They're just descending now on that heat shield. The next step will be straighten up and fly right. They'll eject a few more masses.
About 550 meters per second at an altitude of about 15 kilometers from the surface.
So we've slowed down by a factor of 10. They'll eject a few more giant blocks of tungsten that they've carried all the way from Earth to Mars.
We are coming upon the start. We are starting the straighten up and fly right maneuver,
jettison,
where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Doppler indicate shoot deploy.
Shoot deploy.
Navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Parachute is the scariest part of this landing, I swear, because I've seen more parachutes shred in simulations and in tests, and the fact that it's working is a massive relief.
Perseverance is now
heat shield
slowed
separation.
to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
They're using radar to detect the range to the surface. They're going to take photos with a down-looking camera, compare them to maps on board the spacecraft that geologists made, mapping the surface and identifying potential hazards in the landing zone. And they're going to try to steer for safe places in the landing zone. That's called terrain relative navigation, and it's an innovation for this mission, never been done before on Mars.
3.3 meters per second,
Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars.
Radar lock
Perseverance
also
is
so
continuing
important.
to
Got to know where the
descend on
ground is.
parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Only 4,200 yards, 4,200
We have
meters above the
confirmation that
surface.
the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming.
TVA is nominal.
We have priming of the landing engines.
Terrain relative navigation worked. We know where the surface is. We know where the hazards are. We're steering now toward the safe parts.
83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
Back shell separation, divert maneuver, get away from the back
We
shell.
have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars.
SDS level.
Constant velocity
104.
accordion. Constant velocity accordion, altitude air.
We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct to Earth tones.
Throttle down.
As expected.
Sky crane maneuver has started. About 20 meters.
Tango Delta.
Touchdown! They did it!
Nominal.
Nominal. Yes, I needed that word.
We're getting signals from MRO. Bring you stable.
UHF is good.
They are on the surface of
Touchdown
Mars,
confirmed.
radioing.
Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life. At this point, the descent stage has flown away to a safe distance. Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth.
It's a good day. We have a rover that is talking to us still after touching down on the surface. That's all you need, as long as it's talking
Still
to
getting
us.
telemetry from the lander. All right, all stations.
Touchdown confirmed. We're going to wait for the images.
All right. Sounds like we're going to get pictures. We should get a couple pictures from one of the hazard cameras on the belly of the rover. It will still have lens caps on, so it'll be dusty. Hopefully we'll see wheels on Mars. Come on. Let's go, Mars Reconnaissance Orbiter. Get us those pictures.
OL3, OL1, you have what you need?
We know what that means.
What I need. Flight, we have seen the completion of EDL 3000.
Copy.
Copy activity. That is as expected.
Big sigh over the Boca. So the landing team is done with their work.
From the lander.
Outstanding.
Flight, this is OL3. I am ready to share.
OL3,
They
you're
got
go.
pictures.
For those on M.
All stations stand by for the images. Yes!
Come on, show us the pictures. All right, so we are seeing a hazard camera picture. It has a curved horizon because it's a big fisheye camera. We see horizon.
Flight, this is OL3.
The sky is where it ought to be.
I have the target point on the map when you are ready.
We are ready, OL3. Go for it.
Where did they land? They're. Come on, cameraman, show us the picture of where they landed.
Flight, I'll be moving in, showing you the safe zone that we've landed in.
Oh man, that's a glorious picture. Look at that. So that's a HazCam view. We've got rover deck above us. We've got rover shadow. You can see the arm of the rover. Flat as a pancake.
OL flight.
Unfortunately, I did not see where exactly we landed in the landing ellipse.
TRN.
They're chanting TRN, terrain relative navigation. Must be a good spot they landed in.
Activity, this is OL. Can you repeat that request on N20 EDL off?
OL, can we get the other image to show the cliff?
I'm sorry, say what image again? I'm not understanding.
Flight OL3. OL3.
I like that this is fine dog emission
we've
control.
landed about 35 meters from the nearest rocks that we could identify from orbit by their shadows. Copy OL3, TRN in action.
Yep.
So if I understood that correctly, they have landed in a place that is very close to some good science
I remember
rocks.
this spot. It looks good.
But they haven't shown us a map that I can understand yet, so unfortunately I can't tell you.
I'm sure that you have seen them all and you recognize them all. So,
Whoop. So I believe this to be a rear HazCam. I actually don't know which HazCam images we were looking at before. We see wheels on the ground, which is so exciting to see. We see horizon above.
Flight, we have seen the transition to surface. EDL is done.
EDL is done. So the rover computer is switched over to being a lander computer.
All stations are...
MRO.
And they say, thank you, MRO. Thank you, Mars Reconnaissance Orbiter, for the images.
Congratulations, Perseverance team, and the whole team that's not here as well. Excellent job.
All right, so that's it. It's over. It was successful. We have a new science spacecraft on the surface of Mars sending us glorious pictures. I can't see where we are on that map, but I'm sure they'll send it out on the internet fairly soon. So that'll be the first thing I want to find out, which is where exactly in that landing ellipse we landed. But we already...
we have transitioned to surface as reported downstairs. If you're part of that story to the surface team, make sure you're starting to work those inputs, please.
And that was just Voca telling everybody to get back to work if they're on the surface team. Because they have a rover to set up. They have a bunch of very important things to do over the next couple of days. They have to raise the high gain antenna so they can do high data rate communications between Earth and Mars, get all the commands up to the spacecraft that they need to do. They have to get the mast up that raises all the cameras up above the surface so they can see around them with those beautiful color cameras that Brian told us about. They have to do various other configurations to get some equipment ready in order to operate on Mars. They have to unlock the steering actuators and the wheels, and they'll wiggle the wheels in place over the next couple days. They also will have to do a big software upload to the spacecraft. The upload is probably already done. They probably have the software waiting in the rover computer. But until now, the rover computer has been running an interplanetary spacecraft. It has to transition to become a surface Mars mission, and that's going to need new software. So they're actually going to spend several sols, several Martian days, doing an OS upgrade, which is not very exciting, but I think it'll be taking place over the weekend, which will give some of the science operations people a little bit of a break before they start really digging into the meat of Mars operations on the surface. They'll have about a 30 Martian day checkout phase, where they will go through all of the functions of the spacecraft. They'll take their first drive, they'll wiggle the arm around, take it out and kind of look at all the instruments, test out the instruments on the arm, but not yet on a rock. the next thing that they will do after the first 30 sols are over is they're going to test out the Martian helicopter. They have a 30 sol period for that.
I read you 5 by.
I just want to announce to everybody I've taken a first pass at the surface transition report. I've got some numbers from the script, and I'm awaiting inputs from a couple people still and confirmation from others. It's ready for review.
Yeah, so they're getting down to work on the science on the surface of Mars.
It's ready for review. Are you asking people to take a look at your CASHA report?
That's right. It's ready for review. I'm looking for confirmation from a handful of folks on some of the values before making it final.
Copy. Do you want that confirmation over this net?
The process is to work it over email. I've sent out an email that they can reply to.
Thank you.
I love the banality of administrative work right after a Mars landing. So I think it probably is all over. But for the celebration, I think we can probably take down, well, actually, no, leave the audio up because who knows, there might be some fun announcements or statements coming out. But I'm going to begin to wind this broadcast down because it's over. It's successful. We have another rover on the surface of Mars. And now we have a multi-year mission to look forward to.
Yeah.
So you can follow along with the drama of the mission, of course, with NASA and the Jet Propulsion Laboratory, JPL. I will be tweeting up a storm about it at Emily Lakdawalla on Twitter. And I will, of course, be retweeting to you a lot of wonderful scientists and engineers who are involved with the mission. A bunch of great humans have had a very good day today. So thank you. Congratulations to all of you and thank you for all your hard work. I know it's been extremely difficult, especially in this year of pandemic, to get even the simplest things done, much less landing a 1-ton spacecraft on the surface of Mars. Everybody involved, just absolute congratulations. Well done. Take a deep breath. You did it, and now you get to go do science. So I'm going to wind down this broadcast now. Thank you so much to everybody who stayed with me throughout this broadcast. Congratulations, Perseverance. Congratulations, NASA and ESA and all the scientists involved in the mission. And go Mars exploration, and let's go explore the entire solar system with as much diligence as we've done on Mars. Thank you, Vice News, for having me, and I'll sign off.